All right, guys, welcome back. Mr. Math here. We're going over AMC 12B 2021 fall. Problem number 17. A bug starts at a vertex of a grid made of equilateral triangles of side length 1. At each step, the bug moves in one of the 6 possible directions along the grid lines, randomly and independently with equal probability. What is the probability that after 5 moves, the bug will never have been more than 1 unit away from its starting? Okay, so let's see. Let's try to draw this situation so we know what we're talking about. So basically, we're on this grid made of equilateral triangles, right? And what's happening is this. Whoops, didn't do that great. Oh wow, sorry. This bug is moving along this grid in such a way that, like, sort of at any point he can go in. Let's say he starts here, right? Well, from that point, he can then travel in any one of 6 possible directions with equal probability. And the question wants to know that what's the probability that he never ends up more than 1 unit away from the starting point? Which, if you think about it, that means we want him to stay somewhere on this purple hexagon, right? We want him to stay on this purple hexagon, right? He can't leave that. If he leaves that hexagon, then, right, then he is more than 1 unit away from the starting point. Okay, so we want to find the probability that he, within 5 turns, stays on this purple hexagon. So I basically, I'm sure that there's very creative ways to solve this problem. I'm not very creative when it comes to probability. My brain doesn't work in that kind of way. I'm trying to learn those techniques, but for now, I'm just, I just sort of, again, like, I brute force the problem. I just sort of build the probability based on what I know. So let's just think this through. So basically, if we think about it, in step 1, in his first move, the bug can go to any one of the 6 vertices, and it really doesn't matter which one he goes to, right? So we don't really care what happens in step 1. It really doesn't matter, right? Because he's going to end up at one of those 6 vertices, and his probability is going to be the same regardless of which one. So we can basically just ignore step 1, right? So then we want to start thinking about, well, what about step 2, right? Well, step 2, one of 2 things can happen. He can either go back to the center, right? And what's the probability that he goes back to the center? Well, he would go back to the center with probability 1 out of 6, right? Because, from any given point, he has 6 possible ways to go, and 1 out of those 6 would be going back to the middle, right? So he has a 1 out of 6 chance to go back to the center, right? Now, that would have, let's just say he does go back to the center in step 2, right? Well, then in step 3, again, it really doesn't matter what happens in step 3. He's going to end up back at one of the original vertices, right? Now, what would happen? Okay, so let's just say, without loss of generality, right, that so starting at the center, right? So here I'll use like a green, right? So he starts here, he goes to, let's say, vertex A, right? Then he goes back to the center, so that's 2, right? So step 1, he goes to A. So let's call the center O, right? So he goes O to A back to O, back to A, back to O, right? So he just basically traverses back and forth twice. O to A to O, O to A to O, right? Now, that would happen with what probability? So, sorry, I'm trying to think how I want to say it. Okay, so step 1, it doesn't matter where he goes. So let's just say he goes here, right? 1/6 of the time, he'll go back to the center, right? Then for step 3, again, it doesn't really matter where he goes. So let's just say he goes back to A. 1/6 of the time, he'll then go back to the center. And then with that, we're guaranteed that he never goes outside of here, because by step 5, it doesn't really matter which one he goes to. He has stayed within the hexagon for 5 turns, right? So we have basically a 1 out of 36 chance that he would just end up right back at that center again, right? By basically just going out and back in and out and back in again, right? Now, but that's not the only thing that could have happened, right? He starts at the center. Let's say he goes to A, but let's say instead of going back into the center again, or sorry, wait, it goes out, back in, out. Okay, so remember, this is the situation in which he goes back to the center. So let's say he goes O, A, O. And then remember, step 3, we don't really care. So let's just say he goes to A again. But in this case, let's say instead of going back to the center, maybe he goes to vertex B, right? So he went 1, 2, 3, 4. This has been 4 steps, right? Because he went O, A, O. No, how did it? Yeah, sorry. He went O to A to O to A to B. So that's been 4 steps so far, right? Now, since he's at point B, and it's been 4 steps, basically we just need him to stay. We need him to traverse one of these 3 paths. So he needs to stay within the hexagon, which will happen 1/2 of the time. Oh, sorry. And now, remember, we wanted him to traverse from A to B. Or remember, he could go either A to B, or he could go over A to F, I guess, right? It doesn't really matter which edge he picks, right? But either way, that would happen 1/3 of the time. So 2 out of his 6 steps would be going A to B or A to F, right? 2 out of 6, or 1 out of 3 times he'll traverse an edge during step 4. And then whether he's at F or B, right? Half the time he will stay within the hexagon, because let's say he's at B, he can either pick here, here, or here, 3 out of the 6. So 1/2 of the time he would remain within the hexagon. And that's in the situation in which he goes back to the center for step 2, right? So now we need to consider, well, what if he did not go back to the center for step 2? What if for step 2, so let's say he started from O, so he went from O to A. Let's use a dark red. So he went from O to A, and then he went to B, right? Or B or F. Because remember, 1/3 of the time he will either instead of going back to the center, he'll go to one of the other 2 vertices of the hexagon. Like he'll go left, or he'll go basically left or right, if we want to think of it like that, clockwise or counterclockwise, right? So that's it. Let's say he's at B now, right? Well, 1/6 of the time he'll go back to the center, right? And that would be step 3. Now, step 4, he can go to any one of the 6 vertices. We don't really care which one. So step 4 we can ignore. But we now know at step 4 he's at one of the 6 vertices. What's the probability that he remains within the hexagon for step 5? Well, like we said before, 1/2, right? For him being at any of the vertices of the hexagon, he has a 1/2 chance to remain within the hexagon, because 3 out of the 6 vertices remain within the hexagon, right? Now, let's say instead of going back to the center for step 3, he went to, let's say, C, right? So he went O, A, B, C, right? So in other words, basically what happens is he came out from the center and just stayed along the perimeter, right? He did not go back to the center, right? So that's going to happen 1/3 of the time, as we said before, because he can either go BA or BC. Doesn't really matter which one, right? So now he's at the edge, right? So again, we will have a 1 out of 6 chance that he'll then go back to the center for step 4. And if he goes back to the center for step 4, we're done, because step 5, he has to stay in the hexagon, right? Because he can only travel 1 space, right? But then, of course, there's that 1/3 chance that he goes one more step along the edge of the hexagon, right? In which case, there's a half chance that he will stay within the hexagon, right? Because, like I said, now he's at point D, and at any vertex of the hexagon, he is a 1/2, 3 out of 6, 1/2 chance of remaining within the hexagon. All right, well, this should give us the probability. If we add these up, this should give us the probability, right? So if we sort of simplify this, right? Well, what do we get? We get 1 out of 36 plus 1 out of 36 plus 1 out of 36 plus, now, remember this 1/3 distributes, wait, sorry. Oh yeah, so this, oh wait, sorry. Yeah, so remember, like, this 1/3 is sort of multiplied by this whole fraction, right? So we have to remember that we're distributing out the 1/3. So we do 1/3 times 1/3 times 1 out of 6. That's going to be 1 out of 54 plus 1/3 times 1/3 times 1/3 times 1/2. That's 1/27 times 2, which is 1/54, right? So we get 3 out of 36, which is 1/12, plus 2/54, which is 1/27. And if we add these together by getting common denominators, this will equal 13/108. So the answer is A, 13/108. Now, again, I know that there's probably like much simpler ways to do this. I know, some people are very intuitive with probability. I am just not one of those people. So this was sort of the best way that I can come up with, but but I'd be very interested to see if anyone can give me a more interesting solution to this problem. So all right, anyway, I will see you in the next video, and thank you.